Testing 1, 2, 3. Do you hear me?
Yes, Doctor.
Assalamualaikum.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And good afternoon. So today we're going to go to the new chapter, which is PID Controller Design. Okay. So in today's lecture, I will talk about some introductions, revisit to the time domain analysis, design with the gain adjustment, improving the steady state error using a proportional integral controller or PI controller, improving the transient response by using a proportional derivative controller, PD controller, improving transient response and steady state error by using a PID controller. And then we will see some techniques on tuning of a PID controller using a Ziggler-Nichols method, okay, or ZN tuning method, and then the applications controller design using MATLAB. Along the way, we explore the examples, okay. So as you know that in this PID controller design, we will use root locus as the baseline to design the controller due to the fact that root locus is a powerful tool in the design of control system, okay, using a graphical method. So we will see 4 design techniques which are listed here: gain adjustment, PI controller, PD controller, and PID controller. And since PID, we have to improve the steady state error and improve the transient response simultaneously. So we have to tune, okay? There is a tuning issue. So we have to tune the PID, okay? To choose the suitable value for the P, for the I, and for the D in order to achieve the improved steady state error and improved transient response together by using a popular method which known as the Ziggler-Nichols method. So in order to do that, as I told you before, in control system, the input play an important role, okay? The input of the system. So some of the input that we use in the control system is known as impulse, okay? Which is suitable for transient response and modeling. Okay, so the shape of the impulse is here, delta t. Okay, so it's a shape like this. Okay, it's very sharp and very narrow pulse. The second one is known as step signals. Okay, this is the most important, the most popular input signal used in control system. Or you can say that it is represent the DC volts of the electrical system, maybe 5 volt, 10 volt, or 1 volt. Okay, the shape of it is like this. Okay, so it's square, right? So it depends. This one maybe 1 volt, maybe 10 volt, and so on. Depends on the designer. The third one is the RAM. Okay, RAM, which is the function of T, U of T, and the shape of the signal is like this. It's proportional. Okay, F is equal to T U of T. The fourth one is the parabolic signals, which is 0.5 T square U of T. Okay, this is the shape of the parabolic, which is suitable for steady state error measurements. RAM, suitable for steady state error applications, and step also suitable for transient response analysis and steady state error analysis. The last one, but not least, is the sine wave, which is sine omega t. Okay, which is the shape of it like this, is one of the input signal for frequency response, which used for transient response, modeling, and steady state error. So I believe that you all still remember what is the definition of poles, zeros, which is listed here. Poles is the roots of the denominator of a transfer function, while zeros is the roots of the numerator of a transfer functions. Poles and zero can be mapped on S-plane, okay, where the symbol is pole X and 0. So it is important in a control system. So let us visit what is the first order system. So first order system is a system that has one pole. So in this scale, sample of it is A over S plus A, where the poles is located on the left half plane. Okay. And if we take the inverse Laplace transform, inverse Laplace, so we will get the response for first order system is 1 over exponent minus AT. Okay, so can you imagine what is the shape of the signals? Okay, the shape of the signals 1 over minus exponent minus AT. Osama Belhad. Absent. Abdul Ghani Said.
Yes, sir. It looks, it goes down.
Goes down. Down.
Yeah. Like a curve. I don't know how to describe it for you, but
Yeah. You don't know how to
Doesn't
describe
it go up instead of down?
this.
down.
Okay. Right. Thank you very much. So second one, and the response is here is the first order system. Okay. So the time response, which is for first order system, is shown here. So it goes up. Okay. Okay. 63% of final value of the time constant, which is 1 over A, the tau. Okay. 1 over A. Okay. So let's say the final value is 1 volt. So 63% of 1 volt is equal to 0.63 volt. Okay. So at this 0.63 volt, it occurred the time constant. Okay. And then there is a rising time for first order system, which is here, rising time, and the settling time, TS. Okay. So usually TR is equal to 2 divided by A, more or less, and TS is about 4 divided by A. Okay, for first order system. Second one is the second order system. So second order system is a system that has 2 poles. Okay, so the poles can be real, the poles can be repeated poles, the poles can be complex conjugate, and the poles can be on the imaginary axis. It depends on the equations omega n square over s square plus 2 zeta omega ns plus omega n square, where omega n is the undamped natural frequency. And zeta is the damping ratio. Okay, yeah. So the response can be categorized into overdamp, underdamp, undamp, critical damp, and negative damp. Okay, based on the damping ratio and pole locations. So we have a 5 category of the damping ratio category. Okay, so in this case, second order system based on the standard second order equation here with the input of 1 volt or 1 over s in Laplace. So let's say we have a 9 over s squared plus 9s plus 9. So this is considered as an overdamped system. Okay, so overdamped system meaning zeta greater than 1. Okay, and it will give you 2 different real pole values. Okay, is a real number for pole values. And then the second one is the underdamped. where the zeta is in between 0 and 1. And the poles is a complex conjugate, okay, as shown in the slide number 9. And undamped is where the zeta is equal to 0, where the poles are located at the top of imaginary axis. Okay, as shown here, plus minus J3, and critical damp is where zeta is equal to 1, and it will give you repeated pole, okay, at minus 3. Negative damp, so negative damp is not shown here. Negative damp is less than 0, okay? It's unstable, okay? So there are four categories here. You can add more for the negative damp, okay? For zeta is less than 0, negative damp. Right, so this is all the 5 categories under one graph. And if the second order system, we have some formula that is represent the rise time, the peak time, and the settling time, including the overshoot. Okay, so the peak time is Tp, pi divided by omega d, pi divided by omega n, 1 square root 1 minus zeta square. Overshoot is exponent minus pi zeta over 1 minus zeta square multiplied by 100. And ds is equal to 4 divided by zeta omega n. So the formula were derived based on the purely second order system. Yes?
Doctor, this formula is the same for all types, right?
The formula valid for second order only.
I mean for critically damp, over damp, and damp, all types, right? Can be used for this.
Now, yes, sure. Okay. Additional pole where the formula were derived based on a purely second order system. Therefore, the formula valid only for the second order system without zeros. Okay. So when there is a zero, so it will be different. However, under certain condition, a system with more than 2 poles, let's say 3 poles, can be assumed as a second order system. Okay. Provided that the complex poles is dominant and the third pole is less dominant. Okay, so in this case, the complex pole that dominate the overall performance are known as the dominant poles. For example, you have a okay. Okay, so okay, and here, and the other one is here. Okay, so you can see that this one okay, this is both a third order system. Okay. Because they have 3 poles. Am I right? Hello? Hello, guys.
Yes, Doctor.
Yes, yes, doctor.
Yes, sir, can hear you.
Don't sleep in my class. Okay. So you can see that both have complex conjugate poles. Okay. Complex conjugate poles, complex conjugate poles, complex conjugate poles, complex conjugate poles. But can you observe that the third pole, you can see that the third pole for case number 1 here on my right, the third pole is very near to the imaginary axis, am I right? And the dominant pole, am I right?
Yes.
Yes.
But as plain on the left-hand side, the third pole is far, far away from the imaginary axis and from the dominant pole. Am I right?
Yes, doctor.
Okay. So dominant mean the poles have a high influence, very high influence towards the output of the system. Okay. So if the third pole is far, far away from the imaginary axis, this one considered as less dominant. Less dominant, kurang pengaruhnya, less influence. That's why it can be approximate as second order. It is a third order, but can be approximate as a second order. And we can use all the formulas of the second order in the previous slide that I shown before. But for this one, third order, you cannot approximate second order because the third pole is very near to the imaginary axis and very near to the complex conjugate poles. So these poles is dominant, okay, have some dominant and have some influence towards the output of the system. Understand? Do you understand the word dominant?
No, doctor.
Yes.
Huh? Omar,
Doctor, how far it is? How far it is should be?
how far? How
Yeah.
far, based on the rule of thumb, is the ratio between the real dominant pole and the third pole is greater than 5. Ratio,
5.
greater than 5. Ni Umar faham tak apa maksud dominant?
Antum. It has an effect of the whole system.
Okay, in
The
marriage,
major effect.
in marriage terms, if the marriage is queen control, what do you understand by that?
Queen control.
In marriage,
The wife is dominant.
the wife is more dominant than the husband lah. Jadi husband follow cakap wife lah. Kalau
Matriarch.
marriage king control, ni Umar,
The husband has control.
more dominance. Okay, on the wife. Okay, is the analogy lah. Analogy. So there we have a 3 case here. Okay, one is this is a pure second order, pure. This one is approximate second order. And this one is pure third order. Okay, so we have 3 cases. Case 3 behave like a second order, definitely. Approximation is valid if the third pole is more than 5 times further to the left. Okay, so further to the left meaning that the ratio is equal to real part dominant pole ratio. What do you call that? This modulus there, positive number lah, divide by third pole. Silap. Terbalik. Third pole value divide by real part dominant pole. Okay, so ratio greater than 5. Clear? Paham? Contoh. Okay, so the dominant pole is -1 plus minus J1. The pole here is -10. So what is the ratio? What is the ratio?
Then. Maybe.
10 divided by 1 kan? So 10, which is greater than 5. Alright. So we can ignore the third pole. But if the dominant pole is -1 plus J1 and the third pole is -2, what is the ratio?
2.
-2.
2 divided by 1 is equal to 2, less than 5, am I right? So this
Yes.
meaning that poles -2 cannot be ignored. This one, pole at -10 can be ignored for second order system approximations. Clear? Akhi, understand?
Yes, doctor.
Sir, can you just repeat the formula?
Sorry, the formula,
Yeah.
ratio.
Yes.
Ratio pole value divided by real part, not complex conjugate have two part, real part and imaginary part, am I right? So real part, dominant pole. The modulus, positive lah, you must take positive number. If the number is negative, you make it positive. Okay, understand? Ratio? Hello?
Yes, yes, doctor.
Use effect to the of the amplitude response, but do not need effect the EQ of the response. By Yani, off your mic. Consider second order system with poles -1 plus -j 2.828. So by adding zeros at -3, -5, and -10, -10, 0, 0. The closer the 0 to the dominant pole, the greater the effect on the transient response. Meaning that -3 give faster response compared to 0 at -5 and -10. Okay, you can see that if we plot the plot the here -1. Okay, so this number, okay. And then we have a 0 at -3, 0 at -5, 0 at -10. You can see that the zeros at -3, which is near to the dominant pole, will give faster response. Okay, faster, you see. 0 at -3, the first curve. 0 at -5, the second curve. 0 at -10 at third curve. And no zero is the fourth curve. Okay. So adding a positive zero, so it will change the response. Okay, so dia akan turun bawah sikit. It will go down, then it goes up again. Okay. If there is no zeros, the response will be like this. Okay. Maknanya there is no going down. But if there is a zeros, it will go down a little bit. Okay. So this phenomenon we call as a non-minimum phase. Okay, non-minimum phase. If the time response have this kind of slope down. Okay. Maknanya there is a zeros in the transfer functions. Steady state error is the difference between the input and the output. So let's say this is your input and you have two output, which is output 1 and output 2. Output 1 is very good because it goes up and settle at the final value, which is equal to the input value, okay, for output 1. So output 1 meaning that the error is equal to 0, okay, which is a 1 minus 1. But for the output number 2, okay, so let's say this is a 0.8, there is a steady state error, which is 1 minus 0.8, which is equal to 0.2 volt. Okay, so we use the step signals where we can calculate the steady state error by calculating the final value theorem, which is ESS equal to limit t towards infinity e of t. Okay, limit SES S to 0. Okay, so it depends on the input and the system type. Okay, and then from this steady state error, we can we use the static error constants, which is known as Kp, Kv, and Ka, where Kp is the position error constant, Kv is the velocity error constant, and Ka is the acceleration error constant with the formula of error when time towards infinity. So far, any questions? Any questions?
No question, Doctor.
Alhamdulillah, okay.
Okay.
I continue. The formula for the time response specifications only valid for pure second order system without zero. Condition for second order approximations: higher order poles are 5 times further in the ratio formula into the left, and that dominant second order poles, and then the closed loop zeros are nearly cancelled by the close proximity of higher order poles. Okay. So how are we going to apply second order approximation? By looking at the figure B and D. Okay, yield a better approximations compared to A and C. So this is the S-plane. So higher order pole is further to the left of the dominant poles. Okay, this is the higher order poles, the third poles, where the black X is the open loop poles, the blue cross is the closed loop poles. Okay, and then the zeros is the closed loop zeros. So higher order poles can cancels the closed loop zeros. Okay, something like this, close together. For example, the zeros is -3. The poles is minus 2.9. 2.9. So it is very near together, like this. Okay, so this one can be cancelled because it's a very near value to each other. So design with gain adjustment with second order approximation. First, you have to design the procedure for your higher order system. Sketch the root locus. Assume the system is a second order system without zero and find gain to meet the specification. And then you justify the second order approximation by finding higher order poles. Okay, 1, 2, and 3. Examples. So you are given examples here. Okay. The open loop transfer functions is K divided by over S plus 2, S plus 4, and S plus 6. So when we multiply, you will get S cubic. So this is a third order system. Third order system. Okay. So no zeros. So sketch the root locus. Macam mana rupa root locusnya? How is the root locus shape? Sadenan sakit.
Yes, Doctor.
Imagine. Okay. -2, -4, -6. First, we must come up with the rules. Since it's a third order system, the highest order is S cubic, and So how many root locus paths?
3.
Okay, good. So the root locus start from poles, ended at zeros and or infinity. But in our transfer function, there is no zeros, am I right?
Yes, no zeros.
So definitely 3 root locus paths will ended at infinity.
Infinity.
Kan? Okay, one is here, and one is here.
And the other one will go to infinity.
Yeah. There is birds around you, Sadhana Sakit. Are you in the village?
No, doctor, I'm in KD or UT.
A lot of birds outside there. Correct. Okay, so that is the shape. Okay, the freehand draw. Sketch the root locus. Okay, so we compare the computer plot here. Okay, so I hope you know already how to plot this using MATLAB. Okay, remember? Just asking lah. Tanya Nur Farah Arisha. Tak, Nur Farah Arisha. Tak datang. Tak datang Nur Aina Syafiqah.
Yes.
How to plot this using MATLAB, the command com? S.
S equal to TF S G equal to S plus 1. Apa tuh? Yang salah tuh?
S cubic. S cubic
S
and
plus
12 S square. Can? 44S plus 48. Can?
48.
Plus
R locus G.
R locus.
G.
Very good. Very good. Okay. Then we plot the open loop transfer functions, sorry, the closed loop transfer functions of this particular GS. Okay. Unity feedback kan? Unity feedback. So we plot the time response. So in time response, you must plot in the closed loop manner. You cannot plot in the open loop manner. Okay, so in this case, the time response for this is the closed loop. Okay, meaning that C over R is equal to K kan S cubic plus 12 S square plus 44S plus 48. Okay. Plus 48 plus K. Okay. And you assume K is equal to 1. Okay. You assume K equal to 1. So it will be C over R 1 over S cubic plus 12S square plus 44S plus 49. That's why when I plot this closed loop transfer functions, closed loop response, closed loop transfer function time response, okay, n equal to 1, the denominator is equal to 1, 12, 44, 49. 1, 12, 44, 49. Step and D. So that's why you get this value. Okay, the time response value. Okay, so from the time response value here, okay, more region, more region, more region. Ada? Set fun lah. Belum pukul 1 lagi mah. Mau Jun? Tak ada kelas. Lo
Yes, doctor. Yes, doctor.
set fun lah. What is the value of the steady state error? Unity feedback gain, input 1 volt. Atau
0.99796.
oh, you get that
1 minus the final value.
0 to 04.
Yes. 0.9796.
Okay. So this is the response, right? So it's given here, the spec is 10% overshoot. Okay, so 10% overshoot, we have to find the value of K. Okay, so the value of K. So 10% overshoot is equivalent to the zeta 0.591. So by using a standard graph, 10% is about here. So you use your ruler. Okay, goes down. So it will give you the value of 0.591 or more or less 0.6. Okay, the equivalent zeta value for 10% overshoot. Or if you don't want to give a graph or you don't have this graph in the attachment of the test and exams, you can simply use this formula. Overshoot percentage of overshoot equal to exponent power of minus zeta divided by 1 minus zeta square multiplied by 100, or zeta straight away using a formula here. LN stands for what? Alicia Zaidi. LN.
No.
I hear you.
No.
Good. Pinjaman, PTPTN, pinjaman JPA, loan.
Tahu tapi calculator loan juga.
Tak dengar. Nur Izzah Hakimah. What is LN?
Natural log.
Natural.
Logarithm.
Okay. So, well, after you plot, and then the locus, then you have to find the damping ratio line at 0.591. So this is your zeta 0.591. So in order to plot the zeta line in the using MATLAB, okay. So what command you use? Lukmanul Hakim. Lukmanul Hakim. Tak datang. Bantal's iPhone. Bantal's iPhone. Who is this? Bantal's iPhone. Asim Jamil. Asim Jamil. zeta 0.591 as grid z comma 0. So you will get this line, okay, the damping ratio line. So the damping ratio line will give you the dominant pole over here, which is minus 2.03 plus 2.77 J 2.77. Okay, with the frequency omega n 3.43, and the gain K is 45.6. Okay, 45.6. So in order to calculate the gain K at this dominant pole, okay, so we can use MATLAB, or you can use the K, okay, the calculations, okay, the formula, which is K L1, L2, L3, because all our answer is due to the pole's value. Imran Hakimi. Imran Hakimi. Imran Hakimi, tak datang.
Ya, hello.
L1 tu macam mana kira? L1?
L1 apa tu?
2.77 square.
4 plus 4 square.
Okay. L2?
L2, oh,
Abdul Rahman Syarudin. L2. Tak datang.
Ada.
L2.
4.
2
2.
L3. L3. Yusuf. L3. Yusuf.
2.77.
Okay, so you multiply, you get K is equal to 46. Okay, so we stop here, okay, at slide 29. We will continue again next week because it's already 12:50. Okay. All right, guys. Okay.
Doctor, I want to ask. The pole negative 2.03 plus J 2.77, is it possible to find it without using MATLAB, or can we do it by hand, or?
Okay. Who's on the line? Name?
Zenghan.
Huh?
My name is Zenghan.
Zenghan. Okay. We have two ways. One is using MATLAB. Fine. In the test and exam, no MATLAB. Am I right?
No MATLAB.
No MATLAB. So only online exam question or test question, isn't it? And they will give you the plot.
Oh, okay.
Okay. They will give you the plot. Okay. Okay. They will give you the plot. Something like this, Okay. So yeah.
Yeah.
Okay. And then they said 10% overshoot. So 10% overshoot is to the zeta 0.6. Am I right?
Yes.
Okay. Theta inverse cos 0.6. How much?
Inverse cos 0.6 is 53.13.
53 degrees,
So
you have to kena ada ni, apa ni? Protector.
Yeah, protector.
They will give you in the real scale.
Okay.
Real scale, so you have to print. You have to print this. Okay. That's why you need to buy a printer. If you can, please buy a printer or whatever it is. If not, you have to use and put on the screen like this. Okay. So if you have a printer, you buy a printer. Okay. If you don't have a printer, please borrow from your brothers or sisters so that you can print out the graph and then you measure the 53 degrees, and you get the point here, which is equivalent to the MATLAB point. Okay. Did I answer your question?
Yes, thank you.
Sure. Any more questions?
Yes, doctor. I had. Okay.
Name.
Okay. So what I want to ask is like
Name, please.
Theo.
Yo.
Theo Sun.
Yes, Theo.
So we have to bring the protector to the exam, or already decide our exam will be online?
Exam will be online. At the moment, exam will be online, but I don't have any ideas. Is there face-to-face or not? The exam will be in July. Okay. Sorry. Yes, in July, 4th of July. We never know what will happen in July. Is it PKPB or PKPD or PKP? Okay, so either it is MCO or conditional MCO or recovery MCO, we never know. But at the moment, it's online. So I'm answering to the answers just now. We have to print.
Yeah.
Okay. So your question is? What's your question?
So we have to like get something like the protector.
You must have the protector inside your pencil box. You borrow from your brother, like junior brother, sister. They use it in the school.
All right.
If your handphone can measure, okay. Can your handphone measure the angle?
Cannot. Okay. Thank you, doctor.
All right. Any question?
Doctor, I have a question.
Name?
Tekpal.
Tekpal Gil, yes.
Regarding the additional zeros, right?
Yep.
What does it mean by a positive zero? Does that mean a positive zero is on the zeros on the right half plane, or?
Positive zero meaning the zeros on the right half plane. Negative zero meaning the zeros located on the left half plane.
Oh, okay. So that means if a zero on the left half plane and if it's near to the dominant, that means it will go faster. And if it's on the right half, it will go down and then come back up. Okay.
Yeah.
Okay. Thank you, doctor.
Any more question? Okay, no more question. So it's time to makan. Ta'am, set fun, syuru syapadam. Okay, any more questions? So I will see you inshallah next week. Okay?
Okay, doctor. Thank you.
Thank you, doctor.
Astaghfiruka wa atubu ilaik. Thank you very much.
Thank you.